Okay, thank you, everyone. Thank you for coming, and thank you to Melissa for continuing to organize the MSR Crypto Colloquium series, and for for helping to invite visitors. So today we're very pleased to have Professor Shi Bai visiting us. I think this is his first visit to Microsoft Research here. Very pleased to have him. So he's an assistant professor at Florida Atlantic University. Before that, he did a postdoc in Auckland University and also at École Normale Supérieure de Lyon.
Yeah.
So thank you very much for coming.
Okay. Thanks very much for the introduction, and thanks very much for the invitation from Christine and from Hal. It's really nice to visit MSR here. Okay, I'm going to talk about lattice algorithm for variance of LWE. Thank you very much. There must be something dangerous in my slides. Okay, I'm going to start with definition of LWE and CIS problems, and then only after that I'm going to introduce the lattices. So my intention was trying to convey the message that the lattice attack is not the only attack to LWE and the CIS problems. So the lattice attacks have some good features, but they are not the only options for attacking lattice-based schemes. And then I'm going to talk about the general structure for solving LWE. I'm going to divide that into two steps. The first step I call it strategies, and the second step I call it the uSVP and BDD solver. So we combine them together to solve the LWE using the lattice-based method. And in the end, I'm going to give some questions and future topics. Okay, LWE. I'm going to give write out the matrix form of LWE. So sample uniform matrix A from integers mod Q, dimension m times n, where I usually require m is bigger than n for the LWE instance to making sense. And then I will sample S according to some secret distribution, where the distribution is to be specified later. I'm also going to sample small error according to some error distribution DE. So the matrix version of LWE problem is to recover S or E given A and B, where A and B are called matrix form of LWE samples. As a typical parameter, given the input security parameter lambda, I usually take n as the state function of lambda, and take Q to be polynomial in terms of n, m to be not really far from n, and the secret and error distribution respectively from uniform and discrete Gaussian. But these are just one typical choice for LWE, and they are really conservative parameters. In practice, in order to enable more functionalities built on LWE, we will need more secret and error distribution. So I'm going to talk about that later. So this is a visualization of the LWE problem. So given the uniform A, I have secret S and E, and B is given, so the problem is to recover S or E given only A and B. So the decisional version of the problem is given samples A and B, either they come from LWE samples or they come from uniform samples. Decide whether they are coming from LWE or uniform. So there's a reduction between search version to decision version and vice versa, which is trivial. But there might be some loss during this reduction. But in practice, we could either solve the search version or decision version. Okay. So in order to introduce the strategies for attacking the LWE problem, I'm going to introduce the dual problem, which is called the SIS problem, or inhomogeneous short integer solution problem. So the problem is really due to the LWE problems. Let me get to the next picture. So the problem is given B, which is a wide matrix. You can consider this as the transpose of the matrix A in LWE sample. And given the target T, the problem of the CIS problem is to recover the E such that BE equals to T mod Q. So that's a dual problem to the CIS problem, to the LWE problem. Okay. Okay. Variance of LWE As mentioned, in order to enable more functionalities for cryptographic schemes built on LWE, we're going to choose the distribution of S and E from a variety of choices. So the textbook one is to choose S to be uniform and E to be small. So small here means standard, means Gaussian distribution of variation, not too small. Well, that's what small I mean here. And also there's a normal form or Hermite-normal form LWE where the secret distribution follows from E. So I say both of them are small. There are also binary error versions LWE where the S is uniform, but the error is tiny. Tiny means binary in this typical case. There are also cases where I require both of my S and E to be tiny, which are both binary. Of course, there are also binary secret-only LWE where E is sort of standard, so small means standard over here. For more functionalities, such as the for homomorphic encryption scheme, sometimes we need S to be extremely small, like S to be sparse, and E to be relatively small. So here, the variance, I only classify the variance according to the distribution of S and E. So in practice, there could be a different situation with the number of samples given for your LWE programs, or the size of the modulus Q. So all of them becomes useful for typical or specific schemes. They are supported by functionality. So there are lots of applications for LWE, such signatures, encryption, homomorphic encryption schemes, including the seal developed by Microsoft. And these combinations of secret and error distributions, the number of samples given, and the modulus Q, they give variance of LWE with variance difficulty. So the concrete security level needs to be carefully analyzed, even though asymptotically, sometimes they don't really differ too much. OK, so before I start to describe the lattice algorithm, which I classify, which I presented as a geometric algorithm, there are broadly 3 methods in the current literature to solve the LWE problem. So the first one is so-called the algebraic attacks, which arise from the initial work of Aurora Ge algorithm and their variants. And the combinatoric algorithm follows from the original work of BKW, as well as meet-in-the-middle-like algorithms. And the geometric algorithm is to freeze the LWE problem or the CIS problem as some lattice problem, and then solve this problem on lattices. So this is not necessarily the best method to solve LWE, but this is just one alternative method. That's why I list all of them comparatively. So in this talk, I'm not going to consider the structured LWE problem where, because of the reach of the structure, there could be some other attacks. In particular, when this structure are involved with the error and the secret distribution, there could be some either attacks. So some of the works can be found in the literature where I'm not going to discuss that in this work. So in this talk, I'm going to focus on LWE in general Q-array lattices in this talk, where the definition of this will be given quite soon. Just a very quick summary of algebraic attacks for LWE problem, where I mentioned it follows from Aurora Ge algorithm. It's particularly useful for the LWE problem where the error is really, really small. For example, for binary error LWE problem, the running time is already polynomial as long as the number of samples given is more than quadratic. So it's quadratic. So that's the current state of art. And as soon as the number of samples is slightly restricted to be smaller than the quadratic, we still have a substantial algorithm. This is by the Grobner basis algorithm of these authors. On the other hand, there is a reduction from the worst case hard problem with polynomial gamma, but in dimension n over log n, as long as m is slightly larger than n. So the number of samples given is slightly larger than n. So by looking at the best attacks here and the best reduction here, there's still a gap between the number of samples of a little bit more than linear compared to this one, compared to this linear one. So the best attack still does not match the best reduction for the moment. So there might be a gap in between. So as soon as the error becomes larger, so it becomes it's more than the binary, then this Aurora or algebraic attacks are becoming harder to solve the LWE problem. So the rule of thumb is the running time is 2 to the tilde order, which wraps the logarithm of this part, of alpha squared q squared, where alpha is the error rate for the LWE problem. So this already becomes substantial when the deviation for the error or approximately alpha q is smaller than square root of n. So that's smaller than 2 to the n. That's already substantial. However, for standard error LWE, where the error is small or from Gaussian, so this algorithm runs in 2 to the n log n, which is even slower than the saving algorithm. Okay, so that's the current state of algebraic attacks. So in the second class of algorithm, which I call the combinatoric type of algorithms, which originally follows from the BKW algorithm, it does something similar to the Gaussian elimination and use that to do a dimension and error trade-off. So that's the basic idea of this combinatoric algorithms. In the extreme case, if we treat the LPN as a case where the Q is 2, then the BKW algorithm already runs in substantial time, which needs exactly the same number, asymptotically the same number of samples. And in a paper by Lubishevsky, if he has some kind of sample expansion technique, which simply combines samples with a sacrifice on the increase of the error. So this gives a slightly worse running time. However, this only needs slightly more than a linear number of samples. For binary secret and error LWE, the best attack is from Kirchnell and Fook. They use kind of BKW variant, but they don't allow, they extend this BKW kind of algorithm to have a running time of 2 to the n over log n. Okay. So as far as I understand, this still does not match the best reduction, where the reduction says it's 2 to the n over log n, so there's still a gap over there. And for the standard LWE, so that's pure exponential time. There's also the middle type algorithm, which does the memory and time trade-off. They are typically used for sparse secret and E. We're going to mention some of them later. Okay, so the third category or class of algorithm is the so-called geometric algorithm. Essentially, I mean the lattice algorithm. They turn the LWE problem into problem on lattices, and then solve it either using lattice reduction algorithm or lattice saving algorithm. So the main feature is that in this type of geometric algorithm, the LWE samples required are usually small. So if this is the case, if the number of LWE samples are restricted, some of the previous algorithms, like the combinatoric algorithm, does not usually work very well. And in this case, it is the lattice algorithm which works usually better. On the other hand, asymptotically, if I only use the lattice algorithm for attacking the LWE, the asymptotic running time is not really as ideal as the other algorithm. For example, for LWE, binary secret error LWE, binary secret but small error LWE, or binary secret but small uniform secret LWE, or the sparse LWE, whatever kind of there must be something important in the slide that I don't want to show. But, oops, I trigger some. Okay, so for all of these variances of LWE, the asymptotic running time of lattice algorithms are all fully exponential. So in this case, the lattice reduction algorithm or lattice saving algorithm does not really take advantage of the small secret. Probably that's also, the restriction also comes from the number of samples it uses. So in this lattice reduction algorithm, the number of samples it uses is usually small. So in the information theoretical point of view, it does not fully use all the samples compared to the previous combinatoric algorithm. On the other hand, if you allow large modulus, for example, if the modulus goes to exponential, but with small errors up to some extent, then there's a polynomial. The algorithm, the lattice reduction algorithm, already run in polynomial time. This was explored in this paper. Okay. However, these lattice algorithms are most relevant in terms of concrete security levels to give a concrete security for practical schemes. Okay, so a very quick introduction on lattices, because we only use lattice now. Integral lattice is the object that we are interested in this talk because I want computer representation to be efficient. So this is a integral linear combination of vectors, bi, where each bi coming from that n. I assume it's a full rank lattice in this case. And just notation purpose, I take all of the basis vectors b1 to bn, and I call b to be the basis matrix. And the lattice can be represented by having the column combination of b, the integral column combination of the basis matrix b. So that's my notation. Okay, and the volume of lattice is defined to be the absolute value of the determinant of the basis matrix, which is independent of the choice of the basis. So it's up to a unimodular transformation. So the quantity that we are interested in lattice problem is so-called the lattice minimum. So it's the shortest lattice vector except point 0. So in this picture, it's probably this one, because this two-dimensional lattice is probably this one, because that gives the smallest radius. And it does not include any other lattice point except it's the reciprocal of itself and the 0 point, since the definition removes the 0 point. Okay. And the main computational problem on lattices is so-called the shortest vector problem, which will show up in a second. So the input of the problem is a basis matrix B, and the output of the SVP problem is to find a shortest vector in this lattice. So in the columns, in the integral column space of this matrices B. So if we just look at this two-dimensional lattice graph, which are represented by these green dot points, this is really, even visually, this seems to be a very easy problem because this blue one seems to be the shortest lattice point. The main reason is the main difficulty of these problems, of the SVP problems, depends on the input shape of the basis B. So let's compare with this with the other picture. If the inputs are this red and blue two lattice point, then this problem visually seems to be much more difficult compared to the first problem. That's what it means. The difficulty heavily depends on the shape of the input basis. In cryptography, this input basis have some similar kind of shape of this one, where they are very skewed to each other. So they are very far from orthogonal to each other. So the task is to, with that input, recover this more orthogonal lattice basis. So that's the task. Okay. So in cryptography, we need a relaxed version of the shortest vector problem. So the previous problem is called SVP1, where this gamma is some relaxed or approximation factor. So instead of finding the very shortest vector, we are allowed to find a vector which is at most gamma times the length of the shortest vector. That's the relaxed version. So in order to solve the original, the exact SVP1 problem, so the algorithm are enumeration and sieving, but in order to solve this approximated version, which are SVP gamma, there are a variety of algorithms coming from, which ranges from the triple L algorithms and the so-called BKZ algorithm. just a quick summary, the best algorithm for solving the exact SVP problems are the enumeration and the saving. The enumeration algorithm runs in super polynomial time, super exponential time, so 2 to the n log n, or more than single exponential. Where the saving algorithm runs in single exponential running time. So in practice, there was a bit of interesting history that the enumeration algorithm, although asymptotically slower, usually outperforms the saving in practice. However, this situation has been changed since last year, where people found that they can have good algorithms which try to boost the saving algorithm such that it also works faster in practice. So the current state of art between these two algorithms is, in practical dimensions, the saving algorithm is faster than enumeration, as well as asymptotically. So that's the current state of art. Of course, the concern is whether the saving algorithm can be extended to higher dimensions, because the saving algorithm requires exponential amount of memory, where the enumeration algorithm only requires the polynomial memory. On the other hand, the best algorithm for SVP, for the approximated SVP gamma problem, is so-called the BKZ, whose complexity is dominated by the exact algorithm, but in smaller dimensions. So if the dimension for this SVP problem, for this SVP gamma problem is in n, so these SVP problems are usually in dimension smaller than n, maybe half of the dimension for some practical schemes. So that's pretty much the thing we need. And two types of lattices that we're going to use, and they are relevant to the LWE problem. So this is the LWE kind of shape of matrix, which is input A. And the lattices, the Q-array lattice on this A, which I call it as either maybe the column lattice or the image lattice, is the image space of AX mod Q. So the only difference between the column space over the ordinary R is that I have a mod Q here. Let's assume Q is prime. Maybe let's see there, it's over finite field. And then a dual or reciprocal lattice is this orthogonal one, which is called the kernel lattices, because it is the set of all the points E, which cancels out this B, input B. And to make sure these two lattices are non-trivial, so they are not that n, I usually require M is strictly larger than n. That's the case for our input. So if we have a LWE instance, I usually consider this one. If I have a cis input-like basis, I usually consider this one. So that's the two lattices. OK, so lattice algorithm for solving LWE. I'm going to decompose that into two steps. The first step I call it a strategy. So given the LWE problem, there are different strategies to solve the problems. So we can directly solve the problem using some solver or oracle, where the oracle can be some instantiation of the SVP solver or some combinatoric algorithm. So on the other hand, this LWE problem can be first converted into another LWE problem or another ISS problem or cis problem, which I described in the very first part of the talk. And then after that, we use the oracle to solve this problem. So it looks like this detour, we're doing some kind of detour in this attack. However, in certain variants of LWE, such kind of detour indeed gave a better algorithms. And I have a dotted line from the solver to here, which means during this conversion, it could be possible that I use the power of the oracle in order to get this conversion. So some computation, non-trivial computation can happen either on this conversion or either on this conversion. Okay, so the very first strategy is so-called the primal attack. The main features it uses is that in LWE sample, where the AS is very close to B modulo Q up to the error vector E, because the E we sampled is from a small discrete Gaussian distribution. We can directly solve this problem as a CVP problem, the closest vector problem, or the bounded distance decoding problem using the lattice solver. To do this, we consider the image lattices arised from A, which is the column space of A mod finite mod Q. So this consists of all the y such that y equals to ax, where x coming from order that n. And one of these y is going to be close to our B because E is short. And this lattice has rank m and volume Q of m minus n. So to solve this problem, we can convert this BDD problem into a unique SVP problem using Kannan's embedding that I will describe later. But the concrete security depends on the number of samples given. If there's no restriction on the number of samples, then the best choice is to choose m approximately equals to n over log q divided by minus of log alpha, where alpha is the error rate. So asymptotically, the running time with this primal attack is given by this relation. So from this, we can already recover the argument that I mentioned before. If the error and the secret are really, really small, the asymptotics of a lattice algorithm are still fully exponential, simply because as long as Q is polynomial, that this thing becomes the same, has the same thing. It won't change the asymptotics. So the binary error LWE does not change the asymptotics. However, the concrete security could change, of course. Okay. To convert the BDD problem into a unique SVP problem, so the standard way is to use the so-called Kannan's embedding, where I expand this mod cube in the LWE problem by rewriting as B equals to AS plus E plus C times Q, where C is some arbitrary vector. So the argument essentially says the lattice point AS plus this CQ is close to B up to this error vector E, where E is a small shift, where I can embed this small shift E together with another short amount 1 into a lattice generated by a new basis, which I call L prime. So L prime consists of LB01, where L is the basis for the image lattice of A. So if you look at the multiplication, LB01 times this star 1, where this star part is the coefficients generating the lattice point AS plus CQ over there. So L times star equals to AS plus CQ. But it's a negative 1, so I just ignore the sign. Okay. So the second strategy goes from the other direction. Instead of going from the LWE, instead of having the direct decoding attack, I can rewrite the LWE problem in terms of cis problems by multiplying the left kernel of the matrix A over FP. So, and then I will use the solver to solve the cis problem. That's the second strategy, which sometimes called the dual attack because this is really the dual of this thing. So the workflow is simple. So I take the left kernel, which I denoted as A perpendicular times AS plus E. So this part becomes 0. Left over is A perpendicular times E. So this has the shape of the cis problem, where A perpendicular acts as the B. Remember, this is going to be a wide matrix in the previous picture. So the general way to solve this is the general way to solve this cis problem is to solve a CVP problem. So first of all, we find an arbitrary vector y such that b times y equals to t. So there's no requirement on the length of y. Therefore, this step is very efficient. And then I consider the kernel lattices of this b, which consists of all the vectors x such that bx equals to 0. And then I will take some target point y and then call the BDD or CVP solver in the kernel lattice defined by this basis. This will return me a vector v, within this kernel lattice and close to y. And then in the end, I will simply subtract them. Because v is close to y, the subtraction should reveal a short vector E. And assume that the solution is unique in the LWE instance. So in this attack, you can see it's similar to the previous attack in the case that once I did this kind of cancellation, only the information on E is left. The previous decoding attack is very similar, where I only use the information that E is short. Therefore, only the E information on E is used. So this also means if I have a very short secret, or I have some special structure on the secret, these two attacks does not really use that property. In order to tackle that, I can have another attack, which is called the primal attack on a expanded matrix, where I rewrite LWE problem AS plus E as A concatenated with identity matrix dimension M times a very long vector concatenated with S and E. So the root does not change, but it's the way that how we construct this SIS problem has been changed. For example, I rewrite this problem as this one, and then now the new task is to find the short solution S and E in the kernel lattice of A prime. So in this case, since the solution we are seeking for does contain the information on the secret, so the information on the secret is retained, is relevant in the attack. So if the S and E are not balanced, then we can rebalance the lattice, which is the lattice introduced from A and M. So all of these methods we mentioned so far are sometimes equivalent, but not always. As you can see, at least the information on S is relevant in this attack. And there's a fourth strategy, which is kind of repeating what we mentioned before, using the dual attack. However, it does leave the information on the secret. The previous dual attack completely cancels the information on S. However, if we do a little bit of modification on this attack, we can still keep some information on S. So instead of finding the exact left kernel of A, we can find the approximate left kernel of this A, such that if I multiply them together, instead of getting 0, they give me a short vector. So that's the simple modification. So to keep S, we'll find the AT such that we'll find the X such that X does not completely cancels A. However, it cancels A up to a short vector Y. Here, I only require that X and Y are both small. In other ways, I can consider, I can again write this in the SIS form, where I concatenate A. So this thing is going to be a very kind of wide matrix times X minus Y. So if WV is a short solution to X and Y, then I can multiply W on top of V, and as before, this almost cancels up my A, except left this Y, which is this V. So I have V times S plus WE. So WE is the previous thing. In the previous attack, I already have the WE over here. But now, since I do not fully cancel S, but I leave with some V, so I have V times S. As long as my V is short, then V times S is short. W times VE is also short. And furthermore, if S and E are not balanced, very similar to the primal attack, we can rebalance the lattice that I constructed in this step to balance the solution for X, Y. So these two kind of balance are really the same framework, but one applies to the primal, this applies to the dual case. Okay, so the previous four strategies only consider the lattice reduction. Well, in practice, if the secret or error comes from sparse secret, it's usually good to combine that, the lattice reduction with a combinatoric attack. So this line of research was, I think, was originated from the original attack on N2, where they use a bit in the middle attack and then hybrid lattice reduction and combinatoric attack on N2. This was extended to LWE by Woodward, and then extend to other variants of LWE. So sometimes it leads to a better algorithm, especially when S and E are sparse, because the combinatoric algorithm is usually good for sparse secret. So, so this is my personal claim that the aforementioned four strategies can be combined with meeting the middle-like algorithm, although I haven't really fully recovered all of them. Some of them appeared in the literature, but some of these strategies were not combined with meeting the middle algorithms. So maybe that could be an interesting project to work on after this. Okay, so I will just mention one hybrid attack, which follows from the due and distinguisher attack of Algebraic. So very similar to what we described before. So remember before we have this V times S1 plus W times E. So instead of completely recover S as a full vector, so we're going to separate this S into two parts. I call them S1 and S2, which correspond to the left-hand side columns of A and the right-hand side columns of A. So I call them A1 and A2. I'm only going, in the dual attack, I'm only going to find the space for the dual for A1 instead of A. And after that, I got this relation where this part in the parentheses should be short, because that's exactly what we had before. The extra term we have is W times A, W inner product with A2S2. However, now I know what W is because that's from the due of A1. I know what A2 is, so I can just try different values of S2, and hopefully one of my guess is correct. If my guess is correct, then the whole thing over here is going to be small. So that's why I'm saying this in the due distinguisher attack of Algebraic is sort of a dimension and error conversion where I transform the problem into a new algebra problem with a new secret S2, where the samples are given by the inner product of W times A2. So for each guess of S2, I will check if the difference of WB minus that is short. Alternatively, this can be done by using a memory time trade-off. So that's the hybrid attack on this due thing. And that attack can be rephrased in this framework. So given the LWE problem, I converted that into another LWE problem where during the conversion, I need to use the power of the oracle. And then after that, I solve this problem using some combinatoric attack or maybe a lattice attack. So all of them are possible, I think. Okay. So far, I only talked about the strategies for solving the LWE, where I kept this as an oracle. I didn't really open the running time of these solvers. And in this section, I'm going to open that up, just give a little bit of running time on the algorithm for solving SVP problem and unique SVP problem. So the SVP gamma problem, as I mentioned before, is try to find a vector where it's up to lambda times the shortest vector of the lattice. So the main tool to solve this problem is the algorithm called BKZ with some input parameter, which we call the block size, which is the integer, which is usually smaller than the strictly smaller than the dimension of the lattice. Otherwise, it becomes the full SVP. So to solve this SVP gamma problem, so we're going to apply a BKZ algorithm with parameter beta. However, the difficulty of this problem really depends on this approximation factor gamma. So if gamma is really, really large, for example, if it's slightly more than the substantial factor, then we already have a polynomial time algorithm by applying the BKZ beta to solve this SVP gamma problem. However, in cryptography, people usually set this gamma to be polynomial or some slight subexponential, which is way much smaller than this. And in that case, the beta we need to use is really large. And the running time is 2 to some constant c times the block size we need here. So if beta is about the size of n, then we're going to have a full exponential algorithm. where the constant c depends on the algorithm, the concrete algorithm we are using, either enumeration or saving. The previous problem all leads to a special problem which is called the uSVP gamma problem. So this problem is different to the SVP gamma problem in the case that the lattice we have is special. So there is a promised gap between the second shorted vector and the first shorted vector. So the rule of thumb is to plug in this gap gamma into this estimate and use that as the running time of the oracle for solving uSVP gamma. So that's just running time. For example, in the very first strategy, so we have in the decoding strategy, I'm considering the lattice generated by the image of A, and then I'm going to look to solve a problem, a BDD problem, which says the AS is very close to B up to E. So this gives me an image lattice of dimension M, where the gap in this lattice is estimated by this. And by plugging this into here, I can get the beta, and therefore I can get the running time. So this also involves to optimize the number of samples I'm given. As long as we have the number of samples given is big enough, the optimal running time is given by this. And this recovers the asymptotic formula in the very first few slides. Okay, and a little bit more insights on the BKZ beta algorithm. So given a very a big basis, the BKZ beta algorithm smooths over the basis vector with many runs of SVP beta, where it does this continuous SVP beta for each block size of beta. So, and if a single block is SVP reduced, then we have this quantity insurance where gamma beta provides, it's a Hermite constant of dimension beta. It provides an upper bound for the quality of the first vector in the basis. On the other hand, we can have the dual SVP reduced. And once we have all the blocks reduced, they all satisfy this relation, we can link them together to get the quality control for the very first vector compared to the overall determinant. So that's how the analysis goes. And the current algorithm, including BKZ, slide reduction, and self-due BKZ reduction, uses a combination of these two strategies to guarantee the quality of the reduced basis. Globally, it does many tours, and for each tour, it smooths down the basis vector by many invokes of the SVP beta. So that's the just some mechanisms of the BKZ algorithm. So a very simple BKZ algorithm follows the description. Simply assume that this is a dimension of n lattices. Then I will simply do SVP on block size of beta for each consecutive indices starting from 1 up to the n minus beta plus 1. And the blocks in the tail, they are becoming smaller blocks, so I cannot do the SVP beta anymore, so I will just do as much as I can do on SVP on size n minus I plus 1 over there. And after each tour, the basis is smoothed by bringing the shorter vector to the front. And have a movie on that kind of stuff. So these are the starting, so these are the simulation for, these are the actual run for a BKZ 40 reduced basis, where the lattice dimension is 100. And then this is the starting point of the algorithm where I draw the Gram-Schmidt, the logarithm of the Gram-Schmidt of the basis vectors. And after the very first tour, you can see it pulls down the very first Gram-Schmidt vectors and then pulls up the thing in the tail. And then if I continue the tours, it tries to further pull down the very first vectors and pull up the tail vectors. So the vectors that we are most interested in is the very first one, where you can see during this procedure, it's gradually being put down. You can see. So that's the principle of this. Sorry. And that's the end of BKZ 40. There are two tasks relevant to the BKZ. The first one is quantifying the quality of the BKZ, and the second one is quantifying the time of the BKZ algorithm. Where the second task, I believe, which is a much harder task, so I only gave a slide for giving some overview for that. But quantifying the quality for the BKZ algorithm seems to be reaching a stage where we have some confidence to say after BKZ beta, what kind of basis we can expect. So the idea is to consider the average behavior of the algorithm. So although previously we have the upper bound estimate for each local block, so in encryption analysis we are most interested in the average quality of the algorithm. So to do this, we will substitute the upper bound of this Hermite constant at dimension beta by Gaussian heuristic at dimension beta. And we will look at the behavior of SVP in local blocks, and then we will simulate the behavior of tools globally to see what is the end quality of this. So the asymptotic estimate is going to be this one, where the volume is the determinant of the lattice. But we have a better way to decide this Hermite factor, which is to use a simulation. However, in the previous experiments, it has been realized that this average case analysis by using Gaussian heuristic seems to be even worse than practice. Although it was shown that in the study by Gamma and Nguyen that the Gaussian heuristic seems to be pretty accurate. In practice, it has been found that the B1 in the local blocks could be even smaller than this Gaussian heuristic estimate. And this was observed in subsequent works of Chen and Nguyen and Liu and Ducat and Yu. To show this, I just have some picture where I think I can just skip this, where the most important features are the actual Gram-Schmidt, which are in this red line, and this Gaussian heuristic, which are in black. So for average case analysis, we should expect this red line, as long as the block size increases, essentially matches the black line. However, in practice, if I increase the block size, you can see there's a sort of converging phenomenon. However, the actual Gram-Schmidts in experiments are even better than the Gaussian heuristic. So there's the intention or kind of fear to say that maybe the lattice reduction algorithm even works better than the Gaussian heuristic expected. So it seems the average behavior of BKZ algorithm is even better than the Gaussian heuristic. So in our work last year, we tried to explain this using some stochastic models by considering the distribution of the lattices, because the previous estimate used the Gaussian heuristic, which is close to say that, okay, for every local lattices, I pick up the shortest vector to be that fixed value. So our change is really simple. We just take the stochastic model into consideration by saying that, okay, the lattices we have is random. So we assume that's random, and then the shortest vector we generated is also a random variable. So to use that, we are able to have some heuristic analysis using some other statistics. So after k SVPs, the expected length of the shortest vector is given by the previous one, which is either the Gaussian heuristic or the expected value, divided by the number of runs up to 1 over beta. On the other hand, this analysis says that as long as my lattice dimension goes larger, then this impact goes away. So probably this experimental phenomenon only happens for small block size, and when the block size becomes larger and larger, we don't have that concern in lattice-based cryptanalysis. So maybe that was just some kind of double insurance or just some explanation of some phenomenon happened for smaller dimensions. Okay, and the quality I mentioned, we seems to be at a stage where we can we estimate the quality of BKZ reduced basis. However, the time estimate seems to be much trickier, where in order to estimate the time, we have to estimate the running time for single SVP beta times the number of tours. And both of these have some, I believe they have some controversial arguments, and not everyone agrees with each other. In particular, again, there's a discrepancy of whether the local SVP beta cost should be estimated using sieving or pruned enumeration, where although this pruned enumeration gives worse asymptotic running time, the constant on top of this pruned enumeration seems to be gradually decreasing. And at some stage for concrete security estimate, this might be even smaller than sieving. So that's where the main discussion comes from, I think, as well as the number of tours. In some of the models, in the simplest model, where the number of tours is considered to be 1, where the number of local SVP is also considered to be 1, so the overall cost is a single local SVP beta cost. Whether this is true, I'm not sure, because it also depends on the number of tours, which also depends on the strategies. I'm not sure if it can be optimized into stage where a single SVP beta is enough. But on the other hand, it seems to provide a very conservative estimate. So maybe there are also some alternative reduction strategies may reduce the number of tours or reduce the number of reduction we need. Okay, so that's pretty much all. Where I'm going to just have some questions. Some of these are from some of my previous slides. The first question, which I think is plausible, which is a more extensive study of hybrid attacks to LWE using the aforementioned strategies. Because I don't think all the 4 or 5 strategies has been investigated together with these hybrid attacks. Some of this combination could lead to a better attack. Again, there are some gaps between the best attack and the best complexity reduction results in variance of LWE. For example, in binary LWE or in LWE with binary errors, there are some gaps. Estimating the time of BKZ beta is difficult task, so I put it here, as well as the sieving. So one of the issues is for projecting the sieving into higher dimension, of course, is the memory. It's become a bottleneck in real world for large dimensions. Could there be some better strategies for doing BKZ reduction? This can reduce the number of tours. And the last one, how to better use the algebraic structures in lattice reduction for structured lattices. So I don't know the answer for this one. But that's all of my talk. So thank you very much.
Questions?
Yes.
Hi. So you mentioned that for small block size, you have this behavior where the Gaussian heuristic is a bit pessimistic on the length of what we find.
Yes, exactly. That's from experimental study. There are plenty of experiments just to show that if I do this BKZ of small block size, then the very first part of the lattice is even better than the Gaussian heuristic.
And so I guess one way that, well, you said also that this disappears on larger block sizes?
So from this heuristic analysis, we think this behavior will disappear in higher dimensions. So that's our conclusion. Because the only difference, so assume this part is the expected value or the Gaussian heuristic, and dividing out the number of runs in SVP times 1 over beta. So as long as beta comes to larger dimensions, this thing goes to 1. So that's
Do you think there could be any room for like a BKZ strategy where rather than trying to solve locally SVP1, we try to solve some approximate SVP.
Yes, I did mention that although there are already variants which says, okay, so in the implementation, there are already variants which does not solve SVP1, to solve approximated versions. But that's a good question. I'm sure there are other strategies which can probably take the basis in a better way. So the current, maybe the relevant question is the current reduction algorithm only look at the current block while doing the reduction. It does not take the whole basis globally. Maybe there are some global information the lattice reduction can take while doing the SVP reduction on this single block. So maybe that's one road to consider. Okay.
Thank you.
Okay, just.
So there's a particular slide where there's a formula with the complexity in terms of n, q, and alpha.
Yes.
So yeah, so maybe I'm confused, but it seems like with a larger Q, that you actually get like longer running time.
So in this, are you saying in this asymptotics over there? Yes. So if I over here, if I barely plug in large Q but do not change the order, indeed I get a larger running time. You're right.
But from like a learning with errors perspective, with a larger Q, it's expected to be less secure?
Yes, but the optimization, so here I use the gap, which is this one. If you change that, then this asymptotic way to change a little bit. So it's only relevant to the standard.
Okay.
So let's thank Xi again.
Thank you.